I'm very happy and honored to speak to you today. Thank you very much for going all the way to organize this online meeting. I know it's a tremendous organization and a big effort for all of us. So thanks a lot. I would like to talk about the moment problem in infinitely many variables. And this talk is at the same time can be considered also as part one introduction to Maria Infusino's talk, which is following mine. And it is actually a paper that appeared already 4 years ago, so posthumous for Mary Marshall. And I have been talking about it before, but now it has acquired also a new context with the follow-up work with Maria and Infusino and Tobias Kuna and Patrick Michalski, as you will see. So let me start, maybe, okay, if I know how, yes, I know how to do that. Let me start with a summary. I have a bit of trouble here. In this talk, I will present the moment problem for the polynomial algebra over the reals in an arbitrary number of variables. Arbitrary here is the most important word because it will neither be assumed to be finite, not even countable. It can also be uncountable, as you will see. This context is very interesting also for applications. So in that context, we will introduce the notion that we thought at the time is new of constructively Radon measures on topological spaces, in particular on the character space of this algebra, which is just the Cartesian power R to the index set omega. And we will proceed to investigate the relationship to positive linear functionals on the algebra A. The main tools that we will be using are algebraic, and we exploit the localization techniques introduced by Mary Marshall in a series of papers where he was considering the finitely many variable case, and we extended here to the arbitrary many variable case. We will work with this localization of the polynomial ring, the ring B omega, that is generated by the variables xi, but also by inverting 1 plus xi squared for every I. We will show that positive linear functionals on this algebra correspond bijectively to constructively Radon measures on R to the omega, and that the moment problem for A omega reduces to parametrizing the extensions of a positive linear function on A omega to a positive linear function on B omega. Please, if you do not know any of these notions, and I don't expect you to know any, do not stop hearing. That was a summary just of the talk. And I want to here, connected to the next talk, we will observe that this algebra A is the inductive limit of the subalgebras that are finitely generated. And the same is true for the algebra B, the localization. So indeed, many of the arguments will reduce to the finite case. And this last observation was formalized in the projective limit approach that Maria Infusino is going to present, connecting it to so-called cylindrical measures. So that was the summary, and now I want to start really from the beginning with can you see the headings of my, yeah, can you see here history? I'm not sure what you see.
Yeah, we see.
You can see history, the univariate moment problem?
Yes.
Okay.
Yes.
For some reason, I don't see my headings here. Maybe it's too large, the maybe the screen is too large, but anyway, if you see it, that's fine. So let me start with some history. Let us start with the univariate moment problem. So that's an old problem which originates in the work of Stieltjes. So here is the problem for those of you who never heard about it. So you take a sequence of real numbers indexed by natural numbers, and you want to know when is there a positive radon measure mu on the real line such that Sk is exactly the integration over the real line of the monomial x to the ak with respect to this measure for every k. Now, I will recall the definitions later on of radon measure and so on, but since the monomials form a basis for the polynomial algebra, this problem is equivalent to asking something about linear functionals. So let me say the second equivalent formulation. Given a linear functional L on the polynomial algebra R of x, which is a real vector space, when does there exist a radon measure on the real line such that L of f is just integration of f d mu for every polynomial f? That's an equivalent formulation. And there are standard references for the old references for this problem, and I am not intending to give an exhaustive history, just a very short one. Let me jump now to the multivariable moment problem. So now from one variable to finitely many variable, and we are given here a linear functional on the vector space R2 of x1, xn. And we determine also here more the support of the measures. So a closed subset of R to the n, closed for the Euclidean topology on R to the n. And again, we ask ourselves, when is there a radon measure, this time on R to the n, supported on that subset, such that L of f is represented by this measure for all f in R of x. Now, there is a general answer to this, and the answer is due to Haviland, which says that given the linear functional f, such a measure, such a positive radon measure exists that represents f if and only if L is positive on positive polynomials on y. So it's a double statement here. L of positive y is contained in the positive half line, takes non-negative values, where pos y is the set of polynomials in Rx for which f of x is greater or equal to 0 for all x in y. So the set of polynomial positives on y. And there are again general references. I would like here to connect immediately to the context of real algebraic geometry because it was later on in the late 1990s considered by several mathematicians, and I'm not trying to give at all here an exhaustive list. I am sorry for those who are not mentioned there. I'm just kind of mentioning the highlights. Which connected this by considering in particular the set Y to be a semi-algebraic subset of R to the n, and there are various Positivstellensatz, Schmidtgen's Positivstellensatz, Poutinar's Positivstellensatz, Lasserre's work, Mary Marshall's book, that connected also to polynomial optimization, so just as part of the history. Now, what do I want? What is the infinite dimensional or the infinite variable moment problem? Because we consider for the solution of this problem the localization, the R algebra, the localization B, and later on another algebra that we'll call C, you will see later on, we actually need to express this moment problem in the general context of a commutative unital or algebra. We cannot restrict just to the polynomial algebra. So that brings a bit of abstraction with it, but I will try to every time to have an abstract notion to exemplify it by the notions we know. So here is our context. We consider a commutative or algebra A, and now we define the character space chi of A. This is the set of all ring homomorphisms alpha from A to R. Now, the only ring homomorphism from R to itself is the identity, so this is something one can prove. So actually, this is also the character space is the set of all R algebra homomorphisms from A to R. So they fix the reals pointwise. And now for an element A, we define a map which is called the Gelfand transform, which is a hat that goes from the character space to the reals and is defined by duality here. A hat of alpha for a character alpha should be alpha evaluated at A. Now this is not scary. This is like considering the algebra of polynomial. A hat would be the polynomial function on R to the n. So we want to endow this character space with a topology, similarly like we endow R to the n with the Euclidean topology. So we are mimicking this situation here by giving it the weakest topology, making all those Gelfand transforms continuous. And this C of x denotes then the ring of all continuous functions from x to R for a topological space in general. That might appear a couple of times in the talk. That's why I introduced this notation of C of x. So in this notation, A maps to a hat, defines a ring homomorphism from A in the C of chi of A. Okay. Now, let us look at some examples, as I promised. In the case where we have finitely many variables, well, a homomorphism, an R algebra homomorphism from Rx1 to Xn is completely determined by what it does to X1, Xn. So you associate to it a unique point in R to the n. So it is actually just point evaluation, and we see that the character space here can just be identified as a topological space with R to the n. For an arbitrary set of variables, the ring homomorphism, the same story now if you are dealing with the polynomial algebra in an arbitrary many variables, so no relations here between the variables, and can be identified again with point evaluation. So here we have as a topological space R to the omega with the Euclidean topology, with the product topology here for omega arbitrary. And there are two further examples that we are going to dissect later on in the talk. Now, let me introduce two important cones that I am going to use all the time in this talk. One is the cone of sums of squares of the algebra elements, and the other one is the cone of all positive elements or non-negative elements in the algebra, where positivity refers to the positivity of these Gelfand transforms. Now, we want to consider the linear functionals. A linear functional, I'm going to call it positive if it's positive on sums of squares, and strongly positive if it is positive, well, positive here meaning non-negative, if it's positive on the bigger cone of positive elements. These are classical notions from functional analysis that are adapted here to this general context. Now, the general moment problem, I want to express it here in two forms. The first form is the following. We first have to define the notion. So a radon measure on chi of A is a positive measure mu on the sigma algebra of Borel sets of chi of A. So the sigma algebra of Borel sets is the smallest sigma algebra generated by the open sets. There is notion of openness since we have a topology. And we want this measure to be locally finite, that is, every point has a neighborhood of finite measure, and inner regular, which means that each Borel set can be approximated from within with respect to the measure by a compact set. So this is a radon measure on x to the a. And now the moment problem is to consider the set of radon measures which would represent the linear functional in the sense that I defined before of representation. And as I said, this would be called a representing measure. And the problem is, when does L admit a representing measure, a representing radon measure? Now, there is a version of Haviland's theorem that was expressed before for Rx that fits in the general context of an arbitrary algebra that is due to Mary Marshall, and I want to mention in here because it brings up an important point. So Mary Marshall's theorem is that suppose A is an R algebra and X is a Hausdorff space, so think X could be the character space, and hat could be the Galfand transform, is a map, yeah, that's why there was the C of X appearing, is a map from A to C of X, which is an R algebra homomorphism. And now comes an important condition, such that for some P in A, P hat is non-negative on X, and the set Xi, which is P hat inverse of the compact real interval 0I, is compact for each I from in the natural number. So there is that strong condition appearing here. Then for every linear function in L, which is strongly positive, there exists a radon measure representing L. This is a complete generalization to this context of an arbitrary A algebra with that extra assumption on P of Haviland's theorem. In fact, we get Haviland's theorem here by just taking P to be the sum of squares of the coordinates, and then you can check that you retrieve the original Haviland result. A strongly positive linear function on Rx admits a representing radon measure. There is, however, a problem with that theorem, and that's when we started agonizing about this. The hypothesis of the theorem implies in particular that the space has to be locally compact. Remember, the hypothesis of the theorem, I'm going back, tells you that this stratification Xi is a compact stratification of the space, and unfortunately the problems we are interested in do not come equipped with that condition on the space. So there is a price to pay. In particular, that locally compactness never holds on R to the omega as soon as omega is infinite. So we have to pay a price, and the price is to, I am telling it already now, is to give up on having radon measure, to give up on having measures that are defined on the Borel sigma algebra. So let me tell you how we get out of this in the infinite case. So I want to define constructively Borel subset of the character space. So let A be an R algebra, and we look at the following neighborhood, the following open sets of chi of A. So this is for a given A in A. We look at all characters such that a hat of alpha is positive. One can prove that this is a basis for the topology on chi of A. And let us also observe that we can identify the character space, as I said before, for the algebra of polynomials, but this is here in general, as soon as you fix a set of generators with a subspace of R to the omega. And with this, we are interested in R to the omega and observe that sets of the form that I wrote down be in R to the omega for which the summation of bi minus pi squared is strictly less than r, for r and pi in q and I a finite subset of omega. These form a basis for the product topology on R to the omega. Another just a master student exercise, but these two observations together give us something really neat, and this is the following, is that sets of the form that I wrote down here, where you take now not just any hat, but those R minus summation xi minus pi squared with r and pi in q and I a finite subset of omega. So I goes through the finite subsets of omega, form a basis for the topology on chi of A. The word topology is missing. I mean for the topology on chi of A. Okay. Now, all this being said, a subset E of chi of A is called Borel. I'm recalling the definition of Borel. If it is an element of the sigma algebra of subsets of chi A generated by open set, but it is called constructible or semi-algebraic if it is an element of the algebra of subsets of chi of A generated by those special open sets. And it's called constructively Borel if it is an element of the sigma algebra generated by those special neighborhoods that I defined in the previous slide. Now let us have it is obvious here, these implications. If you are in the algebra, you are in the sigma algebra of constructively Borel, and then you are in the sigma algebra generated by open sets in particular, so those implications are clear, but in general the reverse implications are not. However, the case where the index set is countable is really neat, and I want to bring it up here, and I also want to show how we will exploit the fact that the case of countable index set is neat. So this I tell you in this slide. So two important observations. First of all, if A is countably generated, then every Borel set is constructively Borel. So the two sigma algebras coincide. And this is really because of this basis for the topology of chi of A that I have given in that slide 1. Remember that we had rational numbers Ri and Pi, R and Pi, these were rational, so we are counting here countably many things, but also we were running over finite subsets of omega, where omega is the index set. So if the index set is countable, running through the finite sets is still countable, and so at the end you just count, you get countable union, so you get Borel sets. So this is an important observation for things to work. And in fact, the next observation is equally important because of the pullback method. So there we prove, and it is not hard, in fact, I included here a proof, but let me see the time. Perhaps I will skip it and come back to it if someone asks. There is a characterization in general of those constructively Borel sets over an arbitrary index set with respect to Borel sets for the countably generated subalgebra. So let me explain this. A subset E of chi of A, we are now not countably generated, now we are just an arbitrary algebra here. A subset E of chi of A is constructively Borel if it is the pullback of some Borel set E prime of chi of A prime, where A prime is countably generated. That's why I said Borel, and I don't need to say constructively Borel because of the previous comment. And the pullback is for the map pi, the projection map from chi of A into chi of A prime, which is just restricting the characters to the smaller algebra. Okay, so the proof is a one-liner really, and let me proceed for the interest of time. It is some cardinal arithmetic, if you want, countable cardinal arithmetic to convince yourself that this works like that. And let me proceed to the next slide and define constructively Radon measures now that we know what are constructively Borel sets. So constructively Radon measure is a measure that is defined on the sigma algebra of constructively Borel sets, such that for each countably generated subalgebra A prime of A, the push forward nu of mu to chi of A prime via the restriction map is a Radon measure. So we don't just want a positive measure defined on the sigma algebra of constructively Borel sets. We also want it to behave well, to be a Radon measure on the countably generated subalgebras. So what do I mean by this? By the push forward, I'm defining it here for a Borel set Z of the character space of the countably generated subalgebra. The push forward nu is defined by apply mu to the inverse image of Z, where this inverse image is with respect to this restriction map pi. Okay, so we defined everything, and now the moment problem that we are going to consider will always assume that we have finite moments. So let me put this once and for all, and I will not repeat it. We will only consider the measures that we will want to consider Radon or constructively Radon. Will always assume the additional property that at least the Gelfand transforms have finite moments here. So I will not repeat this again. And now, here is the general moment problem 2 in this context, where because in 1 we had the version, Murray Marshall's version of Haviland theorem that works for locally compact spaces, but here 2 is when we depart from that context and we have to work with those weaker measures, the constructively Radon measures instead of Radon measures. So the general moment problem says, we consider for a linear functional on my algebra, we consider the set of Radon or constructively Radon measures which are representing L. And the moment problem is to understand this set of measures, and we are particularly interested in representing positive or strongly positive linear functions. So in the following slides, I will show you the solution of this problem for 3 special fundamental algebras. And these, I will explain why they are so important, but they are also interesting in their own right because they work here as examples. So the first one is the algebra we are interested in, the algebra of polynomials. The second one is the localization that I announced before. And the third one is this very interesting subalgebra, which is the subalgebra of B generated by 1 over 1 plus xi squared, xi over 1 plus xi squared for all I in omega. Now, you might wonder why those, but there is a historical background for this. Well, first of all, let us note that, again, these 3 algebras in the arbitrary index set case are just the direct limit of the R algebras A sub I running over the finite subsets of omega. And now comes the historical reason why we consider those 3 algebras. These 3 algebras were totally studied and exploited in a series of papers ranging from 2003 to 2013 of Murray Marshall, where he solved the moment problems via localization techniques but in the finitely many variable case. But we have this nice property of the direct limit aspect. So we will totally exploit his results, and using the methods that I showed you in the previous slides, we will be able to pull up many of his results. So that's what I'm saying. I will now summarize basically in the next slides properties of A, B, and C and their character spaces and their positive linear functionals and their moment problem that were shown by Mary Marshall for the finite case, and then show you the conclusion for the arbitrary case. So let us look first of all at the character spaces. Now, Mary Marshall showed that you can identify, and that is here not hard to identify this algebra with the polynomial algebra in the variable yizi with I in the index set factored by an ideal, this ideal. Now, the moral of this story is that you can compute the character space explicitly, or that Mary Marshall computed explicitly the character space to be the following compact space. It is the higher dimensional torus. So the torus to the power omega. So it has a compact character space. So we are living here in a compact situation. And moreover, the cone of sums of squares of this very interesting subalgebra is Archimedean. I didn't define the notion of Archimedean. I didn't want to go into this, but I did mention the Archimedean Positivsteinsatz, which comes in essential way here in his considerations. And I see that I have to rush a little bit. And he also identified that chi of B is a dense subspace of chi of C. So this chi business reverses inclusions. The algebra C is contained in the algebra B, therefore the character space of B is contained in the character space of C. And all these potpourri, if you want, of observations but are interesting, bring together to get the results that we want about those three algebras. So the character spaces of A and its localization B, so A is the polynomial algebra and B its localization, are just isomorphic to R to the omega with the product topology. And very important, you have to compute explicitly the difference between the character spaces, because the idea of Mary Marshall is to climb from C to B and then down to A. So you have to do those in a very measured way and know exactly what sets you leave out. So the difference is this, where those delta i's are exactly those characters that vanish on those fractions. So yes, so these are the things I wanted to bring together about the character spaces, and now about positivity. So there is a complete parametrization of positive linear functional on the algebra C. The background is that the cone of sums of squares is Archimedean, so one can prove that a linear functional is positive, so positive on sums of squares, if and only if it's strongly positive, so positive on positive polynomials for the algebra C. The same hold for the localization for the algebra B that is containing the algebra C. Not so, never so, actually, except in the univariate case for the algebra A, that is an old counterexample of Konrad Schmidtgen in a paper in 1979. However, we have still a very nice relationship between positivity of linear functionals on A and positivity of linear functionals on B. And that is this extendability result for a linear functional L on A. L is strongly positive if and only if L extends to a positive linear functional on B. So you see here, on the one end, we have a complete understanding of positive linear functionals on B. And here we have an understanding of strongly positive linear functionals on A via translating it into the positive linear functionals on B. Now, what about the results? What about the moment problem? So let me give them here, and I will try to, if I have time, to show some of the techniques. First of all, the moment problem for C, positive, so positive or strongly positive are the same here. So positive linear functionals on C are in one-to-one correspondence with radon measures on the compact character space. So not only a positive linear function is represented, but it's uniquely represented by a radon measure. Here there is a big use of the Archimedean positive tensors and the compactness of the space. What about the algebra B? Much more difficult. Here we come really to the heart of the paper, the most technical part of the paper, which is a real tour de force from exporting from Mary Marshall's results in the series of papers on localization. So this is the main lemma, which is the most technical proof. For every positive linear function in L on B, there exists a unique radon measure mu on chi of C, such that L of F is integration F hat of C d mu. So this measure represents the Gelfand transforms of elements of C. It also satisfies that all those different sets between chi of B and chi of C are measure 0, and it satisfies a weak representation for elements of B, because here it's not clear, but this is not a Gelfand transform. This is some auxiliary function that we introduced for technical reasons, so we're not there yet. It's a F tilde here. We're not quite there yet, but we can still exploit it as a main corollary here, as a main moment problem for B. We show that there is a canonical one-to-one correspondence between positive linear functionals, which are the same as strongly positive on B, and constructively radon measures. So this is really beautiful, because you see in the previous slide, there was a parametrization of all radon measures by positive linear functionals on C, and here there is a parametrization of all constructively radon measures via positive linear functionals on B. The situation for A is more complicated, and it is our main corollary here. And the main corollary, combining it with what I said before about the extendability, is the moment problem for A. For any linear functional on A, the set of constructively radon measures representing it is in one-to-one correspondence with the set of positive linear functionals L prime on the localization B omega, which extend L. So this, for every one of those linear functions, we can take it here strongly positive, because anyway we are representing by positive measures. For strongly positive, you have to look at the set of all extensions to the localization and represent these and get the radon measure for the character space of A, which is the same as the character space of B, which is just R to the omega. So this is our main results. There is one more main result that I would like to show, and I have shown you the drawback of the version of Haviland's theorem that Mary Marshall gave for a general algebra, however not so general, because it turned out to be that the character space has to be local compound. Now we extended that to the arbitrary situation. So this is the last result that I want to to propose here. So we are still with the polynomial algebra, and the extension of the Haviland theorem in this context is the following. Suppose that you have a strongly positive linear functional, but it is on a closed subset, closed for the product topology, for a special closed subset y, which satisfy a condition that I'm going to give in a minute. Then there exists a constructively radon measure representing it. So here the positivity condition that is in the classical Haviland theorem doesn't give us, as expected, a radon measure, but it gives us a constructively radon measure, provided that the port that we take satisfies a condition, and this is some countability condition. We cannot get away without, and you will see a bit more of this happening in Maria Infusino's talk when we formalize the approach. And the condition is that Y, the semi-algebraic set Y, should be described by countably many inequalities. We do not allow here uncountably many, otherwise we're lost with the argumentation. Now, if we do assume again that the index set is countable, then we are in a much better position, as I indicated before. For the countable case, things work much better, and again you will see in Maria Infusino why this is really formalized and clarified by the projective limit technique that she will expose to us. So in the countable case, we get a better result. We get a radon measure. Suppose that omega is countable, L is linear and strongly positive, and Y is a closed subset of R to the omega. Then there exists a radon measure supported on Y, which represents. So this, for the countable case, is a direct generalization of the classical Haviland from the finitely many variables to the countably many variables. And now my last slide, in the last 2 minutes that I have, is called the cylinder sigma algebra and cylindrical measures. So I was exposing about these results with Mary Marshall in conferences, and I happened to talk to, at that time, strong collaborator of Maria Infusino, Tobias Kuna, who is now our collaborator. And he told me that it rings a bell what we call constructively radon measures, what we call the sigma algebra of constructively Borel sets. It rings a bell to him. It is probably connected to what Laurent Schwartz introduced in his book on measure theory as the cylindrical sigma algebra and cylindrical measures. And that was back in 2016. So we totally took his hint and we worked on this very hard. And I guess the result of this is going to be presented to you in about 16 minutes by Maria Infusino. And that was the end of my talk. Thank you very much.